So in this video, we're going to be talking about Hooke's law. All right. Now, I already made a video regarding elasticity and deforming force. You can watch that video before you move on to this one. So it's a thing of choice. Now, we've heard about Hooke's law. So what is Hooke's law, or what does Hooke's law state? Okay, what's the idea behind Hooke's law? Well, now the condition, provided that the proportionality limit is not exceeded, the applied force, so we can say F, is directly proportional to the extension. Okay, so we can write it mathematically as this. Okay, so provided the proportionality limit is not exceeded. So what happens when the proportionality limit is exceeded? Well, we can say the material no longer obeys Hooke's law. So it's always important to put this. So provided that provided the proportionality limit is not exceeded, the applied force. Now this force, this applied force, it can be a force of extension, or it can be a force of compression. So what am I saying? So let's say we have a spring. So let me go to another page quickly. Let's say we have a spring, okay, a fixed end here. And this is the actual length. Let's say from here, this is L1. Okay, so the force can be extension, an extension force, meaning the force can extend the spring. So it's acting downwards. So we can have something like this. Okay, we'll have something like this. That's 16. Okay, sorry about my drawing. Now we have L2. So a force like this. Let this be F. Let's say F here. And then we have L2. So this is the new length. So you can see the spring has been like extended. So it can also be a compression force. So let's say we have another one here. We have, okay, here the force is going in this direction, and it compresses the spring. So let's let this be L3. Okay, so it can be a force of extension. So this one is a force of extension, while this is a force of compression. Okay, so according to Hooke's law, this force is directly proportional to, okay, this force is directly proportional to the extension. Okay, and then we can write this as, since this is direct proportion, F equals KE. Now this K stands for, people call it a spring constant. Okay, in some situation, or in some resources, they'll write the force constant. Okay, so in some situations, they'll actually write it like this. So you see, maybe in some resources, they'll write it like this: F equals minus kx, or F equals minus ke. So the x is still the same thing as extension, is still the same thing as e. Now, why do we have this minus sign? It's because now this F actually stands for the restoring force. Okay, so just like here we have the extension. Now the restoring force is a force that's going to take it back to the original position. So it's directed in the opposite direction. So that's why you have F equals minus kx in some resources, but you can also use F equals ke, okay, or kx, depending on what resources you are using. Okay, but then this one would just be when we're talking about the restoring force. They're kind of the same thing, just that for restoring force is directed back to its original position. Like if you're going from here back to here. Okay, so you talk about the restoring force. So this is just, so you just have a minus sign here, but it doesn't really change anything in the calculations. Okay, so let's try some questions. Okay, so we have a spring of length 10 centimeters, so we'll write that. We can write it as L1. length 10 centimeter, stretches to 12 centimeters. So our new length L2 will be 12 centimeters. So we can quickly convert this to meters by dividing by 100. So we have 0.1 meter, 0.12. When a block of 3 kg is attached to it, okay, so we have a weight, okay, a block. So the mass here is 3 kg. So we can use, we can choose to, we need to actually, we need to convert this to weight. Okay, what we can do, so we can say W equals M times A, or M times G rather. Okay, where M is the mass, and the G is acceleration due to gravity. Due to gravity. And generally, okay, G is 9.8 meters per second square. Although some resources might put it as 10, but generally, for most problems, you take G as 9.8 meter per second square. So it means that our weight will be 3 times 9.8. Okay, so if we use our calculator, 3 times 9.8 should give us 29.4 Newton. Okay, so this is the weight or the force. Okay, this is the force acting on the spring. So we have 29.4 Newton. Now determine the spring constant A, the spring constant. So using Hooke's law, know that F equals KE. Alright, so what exactly is our E here? So E will be L2 minus L1, which is 0.12 minus 0.1. We can just put 0.10. That will give us 0.02 meters. Alright, so we have our E, we have our F, let's find our K. So again, F is equal to KE, so our E is 0.02 meter, and our F, if you remember, is 29.4 Newton. So we can say 29.4 Newton. If we make K the subject of the formula, so we can, so K will be equal to F divided by E. That will be 29.4 divided by 0.02. So 29.4 divided by 0.02 should give us 1470. Yes, 1470 Newton per meter. So this is the unit for the spring constant, because this is in Newton, this is in meter, so the unit for spring constant will be Newton per meter. Okay, so our answer will be 1470 Newton per meter. Right, so just another question. B. So as what is the extension if the spring is stretched by a block of 4 kilograms? Okay, so we have a new mass, which is 4 kilograms. If we convert this to weight, it will be 4 times, remember, M times G. So that will be, well, where G is 9.8, so 4 times 9.8. And 4 times 9.8 should give us 39.2 Newton. Okay, and then what else? We have our spring constant, K, because 147 Newton per meter. So what we're looking for here is the extension. So E. We're looking for E. So we know that F equals KE. Make E the subject of the formula, and we have E will be equal to F over K. So what's our F here? It's 39.2 divided by 1470. So 39.2 divided by 1470. That should give us 0.0267. I just put everything in at least three significant figures. So 0.0267 meters, or you can put it in two. It depends. 0.027 meters. So you can see the higher the mass, or the higher the weight, the higher the extension. So when it was when it was 3 kilograms, our extension was just 0.02. Now that it's 4 kilograms, our extension is 0.0267. Okay, so I'll just use this. This will be more accurate. 0.0267. That's right, maybe 3 significant figures, and that's it. Okay, so let's move to the next one. So a mass. So let me divide this again. A mass of 2.5 kilograms is attached to a spring whose spring constant is 15 Newton per meter. So we already have our K, which is 15 Newton per meter. What is the new length of the spring if the original length is 8 centimeters? So original length is L1, which is 8 centimeter. We convert this to meter by dividing by 100 to be 0.08 meter. Okay, what is the new length? So L2 is L1 plus E. So it means that we have to find our E first. Okay, and what is the weight? So that W is M times G. Okay, our M is 2.5, and then G is 9.8 meter per second square. So that will be 2.5 times 9.8. So 2.5 times 9.8 should give us 24.5 Newton. Alright, so we have our force. Okay, because here W will be equal to the force. Alright, so using F equals KE, what are we looking for? We're looking for E. So we can make E the subject of the formula. Therefore, E will be equal to F divided by K. What is our F? 24.5 Newton. And our K is 15 Newton per meter. So if we divide this, we have 24.5 divided by 15. Okay, so we get our extension, so E will be equal to 1.633. Okay, 333. So we can just put it as 1.63 meters. So 3 significant figures is okay. 1.63 meters. So this is our extension. But now we're looking for the new length. So remember, L2 is L1 plus E. So means our L2 will be equal to 0.08 meter. Okay, plus 1.63 meter. So 1.63 plus 0.08. That should give us 1.71 meters. So this should be the answer. So L2. I know the extension looks a bit larger than the actual length, but just because of the question. So there's nothing really to worry about. As long as everything is correct. So the mass, calculated the weight of the object, used the formula well, then we have no problems. Then I think we can go to the last question. All right, now this is compress. How much force is needed to compress a spring? So we're looking for F this time, which is a compressive force of spring constants. So K is 10 Newton per meter by a distance of, so our E here will be 2 centimeters. We can divide by 100 to give 0.02 meters. Okay. So how much force is needed to compress a spring? Okay, so we still use the same thing. We know that F equals KE. Okay, so our K here is 10 and our E here is 0.02. Okay, and then 10 times 0.02 will give us 0.2 Newton. So the force required. So you can write this like, maybe if you want to just, give the final answer, you can say the force required to compress the spring by 2 centimeters is 0.2 Newton. Okay, so the force here is 0.2 Newton. Okay, so I think that's it for now. So if you have any questions regarding this topic, you can let me know. Or if there's anything I didn't really talk about, or if there was any mistake I made, then you can let me know. All right, so thank you very much. So in other videos, we'll talk about the curve, the Hooke's law curve, things like that. We'll talk about or the modulus of elasticity. We'll talk about stress and strain. We'll talk about energy stored in the spring. So in other videos, we're going to talk about more and explain more of this. So this is just like an introduction. So thank you and have a nice day. Bye.